Hi students, I am going to explain the working of an NPN transistor in common base mode. So this is the block diagram of an NPN transistor. So you know that there are three terminals for any transistor, namely the emitter, base and the collector. Now in this transistor, the emitter is made up of N-type semiconductor. The base region is made up of P-type semiconductor and the collector region is made up of again N-type semiconductor. So N stands for negative and hence the electrons are the majority charge carriers. And P stands for positive and here the positive charges, namely the holes, are the majority carriers. Similarly, in this N-type, that is collector region, also again electrons should be the majority charge carriers. So this type of transistor in which a P-type semiconductor is sandwiched between two N-type oppositely doped semiconductor is called NPN transistor. Now in this transistor there are two PN junctions connected back to back. So you can see here this P region and N region, in between there is one junction. This is one PN junction. This junction is between the emitter and the base and hence it is called emitter base junction. There is another PN junction between the base and the collector. This junction between the base and the collector, this is called a collector base junction. It is called as collector base junction. So in this NPN transistor, the two PN junctions are the emitter base junction and the collector base junction. Now there are some conditions to be satisfied for the working of any transistor, namely the emitter base junction should be forward biased and the collector base junction should be the reverse biased. So you can very well see here, for that two batteries are being used. They are the supply batteries, namely VEB and VCB. Now the emitter base junction should be forward biased and that is done by the battery VEB. Okay. So what is forward bias? We have already studied. Since the emitter region is a N-type semiconductor, it should be connected to the negative of the supply battery. Okay. Similarly, the collector base junction should be reverse biased and this is done by the supply battery VCB. Since the collector region is also N-type semiconductor, to reverse bias, we have to connect the positive of the supply battery to this N-type semiconductor. Okay. So I have written here emitter base junction is forward biased by the supply battery VEB and the collector base junction is reverse biased by the supply battery VCB. Now we are going to explain how it is working. So before that you should very well know that there are two PN junctions, namely the emitter base junction and the collector base junction. Now due to the emitter base junction is forward biased, the depletion region of this PN junction decreases in width. Similarly, since the collector base junction is reverse biased, the depletion width, okay, or the internal potential barrier width of this PN junction between the collector and the base will be increased. Okay. Now how the working takes place? It is very simple. We start from the supply battery VEB. Since the negative of the supply battery VEB is connected to the emitter region of this transistor, where emitter region is a N-type semiconductor inside which the electrons are the majority charge carriers. So this negative potential of the battery will repel these electrons towards the base region. Say for example I will take that there are 100 electrons in the emitter region. So these 100 electrons will be repelled by the negative potential of the supply battery VEB, so that these electrons will enter into the base region. So you can see that what will happen when these 100 electrons are entering into the base region. In the base region, who are the majority charge carriers? They are the holes. But the percentage of doping is very less in the base region and also the size of the base region also is very less. So the availability of the holes will be less in number. Okay. Say for example, I will take here, there are only 20 holes. Okay. There are only 20 holes in the base region. When these 100 electrons which are repelled from the emitter region enter into the base region, there is a recombination for every electron with one hole. Like this, there will be some recombinations taking place between the electrons and the holes. But the number of holes are very less. For example, I have considered only 20 holes. So, though 100 number of electrons are entering into the base region, the availability of holes is only 20. So, how many electrons can undergo recombination is only 20. So, for example, if 20 recombinations are taking place means, these 20 electrons get reduced. As a result, the remaining 80 electrons manage to enter. They manage to enter into the collector region. So the remaining majority charge carriers, namely the 80 electrons, okay, the 80 electrons will enter into the collector region. Why? Because the collector region is connected to the positive of the supply battery VCB. So these electrons, 80 electrons will be attracted by the positive potential of the supply battery VCB, and they will enter into the positive terminal of the battery. So in the external circuit, these 80 electrons will flow in the external circuit. Okay. Now we started with 100 electrons, out of which 20 electrons undergo recombination inside the base region. Is it not? Anyhow, due to the flow of 100 electrons in the emitter region, there will be a current called emitter current. Since the electrons are flowing towards the junction, the emitter current or the conventional current due to this emitter is flowing in the outward direction. So electrons are flowing towards the base region, means the holes are flowing outwards. Therefore, this is the direction of the emitter current. So when I have represented this arrow mark indicates the flow of positive charges, namely the holes. This is because electrons are moving towards the base or inwards. The conventional current must be outwards. So inside the semiconductor, the emitter current is due to the flow of electrons only. Then in the base region, the 20 recombinations are taking place. So 20 recombinations are taking place, and 20 holes, okay, they disappear, and 20 electrons also disappear. This means that the 20 electrons are flowing outwards. Okay. As a result, what will happen? 20 holes which are missing in the base region, that will be supplied by the positive potential of VEB. So 20 holes are missing because of recombination with the 20 electrons. This loss of 20 holes will be supplied by the positive potential of VEB. So the holes are flowing in the inward direction. So this constitutes a base current IB. So this is due to the flow of holes. So inside the semiconductor, the base current is due to the flow of what? The holes. Okay, after recombination of these holes and electrons, the remaining 80 electrons are flowing into the collector region. As a result, there will be a collector current. The collector current is due to the flow of these 80 electrons, for example. So when I say that the collector, I mean the electrons in the collector region are flowing outwards. That means the 80 holes are flowing in the inward direction. These 80 holes must be supplied by this battery VCB. So I will represent the collector current, the conventional current, the flow of positive charges opposite in direction to the flow of electrons. So this must be the collector current. So inside the semiconductor, the collector current is due to the flow of electrons only. Okay. So again I am repeating. Inside the semiconductor, the emitter current is due to the flow of 100 electrons, and the base current is due to the flow of 20 holes. And inside the collector region, again the collector current is due to the flow of 80 electrons only. But outside in the external circuit, wherever you see means the current is due to only the flow of electrons. Holes can never flow in the external circuit. Only inside the semiconductor holes can flow. So you can see here, this is the direction of the emitter current, okay, it is outward, and this is the direction of the base current, that is inward, and this is the collector current which is flowing again inwards. So if you look at these three currents, namely the emitter current, base current and the collector current, the emitter current is flowing in the outward direction, and these two currents, namely base current and collector current, are flowing in the inward direction. So if you apply Kirchhoff's current law, I can write that the algebraic sum of the currents, namely emitter current, okay, this is flowing outwards. This must be equal to the sum of the base current and the collector current, because these two currents are flowing in the inward direction. Understand? So this equation is true for any transistor in any mode. So we have discussed here the working of NPN transistor. Even for PNP transistor also this equation is true. Okay. Now this block diagram shows that it is connected in the common base mode. So whenever you connect a transistor in amplifier circuit or oscillator circuit or any circuit, out of the three terminals, emitter, base and collector, one is connected to the input, the other one is connected to the output by keeping one of the terminals as a common for both input as well as output. Since this mode is common base mode, the base is kept at the center as a common terminal between the input and the output. So now you can see in this block diagram, the emitter is the input terminal and the collector is the output terminal, and hence in this circuit now the emitter current is the input current, since the emitter is connected at the input terminal. Similarly, IC is called the collector current, okay, or the output current. The collector current also is called the output current. Okay. So for any transistor, we have already studied that there are three parameters or three characteristics, namely the input impedance, output impedance and the forward current gain. Okay students, now in this block diagram, I will take the current gain, okay. So this one is the forward current gain. In this, the current gain is denoted by the symbol alpha. So the current gain is alpha, that is equal to the ratio of the output current divided by the input current. So this is output current divided by input current. So instead of output current, I can substitute the collector current. So this is equal to collector current divided by input current is the emitter current. So this is the expression for alpha. Okay students, and now it has no unit because current divided by current has no unit, and the value of alpha ranges from 0.95 up to 0.99. That means what? From 95% up to 99% of the input current is amplified. That is the meaning. Okay. So this alpha ranges between 0.95 up to 0.99. So this alpha is less than unity, less than 1. Less than unity means it is less than 1. So this is the working of an NPN transistor in the common base mode. Okay students, have you understood? Well.